about to do. Like, well, we're going to keep drawing pedigrees, but we're going to start doing it with harder genetics things, right? So let's at least see. Let's at least make sure that you know what you're doing. Let's start with the what are their names? Giordano or Lutz or Andy, Penny, and Delbert have freckles. So that's probably where you started, right? With 3 shaded in squares and circles. And so there's them. Their mother, Mrs. Cummins, does not. Okay, so they have a mother and father. Mrs. Giordano, Mrs. Cummins' sister, so it's going to be, all right, there, right? She's got freckles, but her parents, Mr. and Mrs. Lutz, do not. Deidre and Darlene Giordano are freckled, but their sister Dixie, like her father, is not. Understand that when we put these up, you can have them reversed. Like you could have put her on this side and her on this side, this whole thing's backward. It's still correct. So don't worry if yours is reversed right to left, like it's still fine. I like to think I have a system where I put the ones that are listed first on the left, but I didn't do that this time. I'm not sure why. You ready for my in-laws? Yeah. Okay. Frank and Marie. So that's my wife's paternal grandparents. Frank and Marie. Frank and Marie, both brown-eyed, and we're tracking blue eyes. So the way I did it was shade blue-eyed individuals. Had 3 children, John, Richard, and Patricia. Of course, you know already that Richard goes by Dick. I told you that story, right? I got that.
Oh, well, we really did.
It's not her fault. So someone was making fun of Papa. All right, John, Richard, and Patricia. So that's them. And John and Richard both have brown eyes. Patricia has blue eyes. Good. Aunt Pat has blue eyes. John marries Diana. She's got blue eyes, and they have Haley, who has blue eyes. Richard marries Nancy, and they have Jan and Melanie, both brown eyes. And then Pat marries Kenny, and they have Claire, Adele, Jake and Annie. Jake and Annie are twins, fraternal, not identical. Yeah. No, Kenny P. Potts. Yeah.
He plays like Brandon instead.
And he's good. All right, so we have our blue-eyed individuals here. What can you figure out?
Frank and Mary are both heterozygous.
So and we're assuming here that big B is brown eyes, right? And little b is blue eyes. I'll teach you the real eye color genetics very soon. It turns out to be just a little more complicated, more like a 2-trait cross. Anyway, we know blue-eyed individuals have what genotype? Like our shaded people, what are they? Yeah. So we can do them first. And that's really, as we move beyond the Punnett square here, doing the ones you know first, especially the recessives, is going to be what gets us there. Okay, then Reagan, what were you saying?
That both Frank and Marie are heterozygous.
Frank and Marie both have to be heterozygous. Why?
because in order to have a blue-eyed child, which is the recessive trait, they would both have to have a cross that would give them the result of a,
Aunt Pat tells us, remember, we're looking for the recessive kid. It's the same thing over and over, right? Like if you just kind of stick with that, about over half of these genetics problems, you've got just fine. These guys have to be heterozygous because that's the only way they can have a homozygous recessive kid. Okay, good. Where else can we do that? Where else can we do that same trick, Riley?
Wife or the husband of the two will be have to be homozygous because they're actually children.
So that's
All the way left.
John.
Yeah.
John's got to be a carrier because of Haley, and you're saying Kenny
Yeah.
because of Annie. Yeah, absolutely. Yep, good, good, good. How about these kids here? Do we know anything? They're brown-eyed, so what do we know from that? One big B. Do we know about their second B?
all their parents have recessive in their thing, so they're more likely to have recessive.
More likely?
It's the only possibility.
It's absolutely certain, right? Because mom, that's Pat, that's all she's got. She definitely gave them a little B. She has two little B's. They're just not showing it because they got the big B from dad. Yeah.
Never mind.
Sure.
I'm just trying to, thinking if they were both homozygous, wouldn't the 3B, big B, little b, but then the 1B, double B, when she's heterozygous? Or something, not, yeah, shit, her.
She's homozygous.
Yeah, she's homozygous, but if she was heterozygous, it would be 3 big B, little B's, and then the third,
Maybe.
well, no.
We don't know that ratios turn out exactly right though. Right?
Yeah.
But anyway, like the way you got to start thinking, and this is why we're moving from Punnett squares, which are about probability, to pedigrees, which are about what do we actually know? What we actually know is that each of these parents contribute one B to each of their kids. It was 50-50 for him, right? So he ended up giving the big B to 3 of them and the little b to 1. It's not exactly 50-50, but you know, that's the way probability works. But her, the probability is 100% she's given a little b. So that little b wound up here, 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 and there. Does that make sense? Is there anything else we know on this pedigree? Anything else we can fill in? Yeah.
All of the ones that are clear, they have to have at least one big B.
One big B because they're brown-eyed. For sure we know that. So we can fill that in. But without any more information, I mean, it's quite possible that we're looking at, it's like a 50-50 shot basically that Dick got a little B here. But we don't know, or we didn't know until this one had kids. That would be my wife. And it turns out when she married me, we had Isaac and Nora has blue eyes. So we know me, we know Nora. Do we know anything else now?
It's probably a recessive trait as well.
Seems likely, although is it for sure? What we know is that Jan has it, right? Because she gave it to Nora. Do we know Isaac? What's Isaac? Well, he's got a big B because he's brown-eyed.
Needs a little B because they're
Same situation it was up here. That's all I have to give. I just have little b, so I gave him his little b. Perfect. Now, but we're still left with Dick and Nancy here. Yeah.
Wouldn't at least one of the parents need a little b so that they could give the little b to the wife?
And that's it right there. One of them, either Dick or Nancy or both, it's possible, have a little b. Do we know which one? We kind of don't. So there's not necessarily a way to do that other than, I don't know, maybe just put like a potential B there and there. It could be big B, it could be little B. We know at least one of them has the little b because they gave it Jan. And Melanie, here we are left with a question. And there's going to be question marks. In fact, technically, these are question marks. All right, so 3 question marks isn't bad. Get used to that. There's going to be question marks on the pedigrees that we do. I will sometimes, to help you out, I'll tell you how many question marks there should be. I'll do that today, but not always. Good? Comfortable with pedigrees? Grab your notes. Let's learn a new genetic pattern. So we are now moving beyond Mendel into non-Mendelian genetics.
Is it actually called that?
Yeah. Yeah, Mendelian is a word, believe it or not. Sounds like what? Chameleon. Mendelian chameleon. I can't imagine you're the first person to think of that, but I've never heard it before. We'll have to look it up. Be a good band name. The Mendelian Chameleons.
Sounds like some form of person.
I want to make the honor.
Boy, George. All right, so we're gonna start. We'll basically do one pattern a day, one curveball a day, one thing different from regular Mendel type alleles a day. This one's called sex-linked. Sex as in gender. These are traits that travel differently through families depending on whether you are male or female. And that's because these are genes. Remember that genes are just locations on chromosomes, right? They're just places, lengths of DNA on particular chromosomes. These happen to be on the X chromosome. That means something fairly normal for females, since they have 2 X chromosomes, but because they're not on the Y chromosome, boys are a little different. Because that means that boys, whereas everybody gets 2 alleles for every gene, we kind of hammered that into you. Not for sex-linked traits. For sex-linked traits, it turns out boys only get 1 because they only have 1 X chromosome. The other one's a Y, and it doesn't have that gene on it. So females show a normal pattern, dominant recessive. They can be homozygous dominant. They can be heterozygous, so they can be homozygous recessive. Males only get 1. You kind of see what boys have right away on sex-linked traits. That's it. Once you get it, it almost makes pedigrees easier because the boys you can do immediately. Because we only get 1 copy, so whatever it is, we show it. If we have a dominant copy of that gene, we show dominant. If we have recessive, it only takes the 1, and we will show recessive. A few times that you don't need 2 recessives to show recessive. The tricky part is we work these. The symbols we use are a little different. We don't want to get tricked into thinking boys have 2 copies. So what we do And really, there's only 3 traits I'm going to make you use that are sex-linked. You'll recognize at least 2 of them. Baldness. You've noticed, right? There's a lot more boys that go bald than girls. Now, part of that is that it's less socially acceptable for females to be bald, so they tend to cover it up. But it is also true that way more men go bald than women. Color blindness, specifically red-green color blindness, not being able to tell the difference between red and green. That is quite sex-linked. It's on the X chromosome. And then, what's that first one? You guys recognize that? Hemophilia, what is that? Hemophilia. It is a blood problem. That's what the hemo means. Not liver. Not exactly. People with hemophilia are missing a particular chemical, a clotting factor. So basically their blood does not clot. Or at least it doesn't clot easily. And so what that means is that people with hemophilia have to be extremely careful about even simple cuts and bruises because the bleeding doesn't want to stop. So it's a pretty dangerous condition. So the way we work these problems is we use what we call superscript alleles. That's just a fancy way of saying you put it in the same spot as exponent, like a squared or a cube, right? And so the allele itself goes in that exponent spot, in that superscript spot. So for example, not having hemophilia is dominant, having it is recessive. But we put it in that superscript spot above the actual X and Y chromosomes. So we don't forget who's a boy and who's a girl. So for example, one possible genotype for a female would be X big H, X big H. She would not have hemophilia. She could also have one little h and not have hemophilia. Or she could have the 2 little h's. That's the only way she's going to show hemophilia. Kind of what we're used to, right? There's 3 possibilities. One of them has her hiding a lowercase h. Boys are simple. There's only 2 possibilities for us. Because we're X, Y, right? Not XX, but XY. That's what makes us boys. So we're X big HY, because Y doesn't have one, or X little hy, and that is all. Okay, you can say that, but like now we have to actually work problems, right? So let's start slow. Two healthy parents. Just use a scrap piece of paper for this. And just do the first one. 2 healthy parents have 2 girls and 2 boys. One of the boys has hemophilia. Make a Punnett square and determine the genotype of the result. See what you can do. I'll help in a minute.
Is this a trick question?
I don't think so. Why? Why does it feel like a trick question?
Because you're a tricky man. Got tricky.
Morning. What, Riley? Yeah, you're gonna want to set up your Punnett square. This might be the last Punnett square we do for a while. You're gonna want the Punnett square to actually have male and female chromosomes there, and these are the places you put the H's, right? And you don't have to worry about the H on the Y. So first of all, it doesn't tell you if the parents had hemophilia or not, right?
I thought they were healthy. Two healthy parents.
Very good. It does say healthy, doesn't it? So what do we know right away?
Don't have it.
They don't have it. What does that tell you about dad?
He has an uppercase H.
He has to, right? If he doesn't have, boys show what they have in sex-linked traits. So there's an uppercase H here. Mom doesn't have it, so she's at least got an uppercase H here. Okay, well, we can do the inside of the Punnett square, at least gender-wise. This is girl possibility, this is girl possibility, this is boy possibility, this is boy possibility. One of the boys has hemophilia. First of all, that implies that the other one doesn't, but we kind of knew that, right? Because she's not got hemophilia. So that means she gave a big H here and here. But one of the boys does. Where's that possibility?
That being the second, thanks, the email is somewhere away.
Has to be. Yeah, has to be. She has to be a carrier for even one of her kids to have it. For one of her boys to have it. Because, yeah, she gives one of her X's to the boy and that's it. And so that means this possibility is that. So there's for girls, what are the odds that either of the girls above is a carrier? Well, what are the odds? If it's a girl, that's these two, that they're a carrier. Carrier means heterozygous, carrying the lowercase. 50-50, right? This is not a carrier, this is yes a carrier. Does that make sense?
So the carrier doesn't mean you have to have it.
Exactly. Carrier means you don't have it, but you're carrying it. You don't show it, but you're carrying it. Yep. And it only applies to recessive disorders, basically, or recessive traits. Now, we did that with the Punnett square. It was kind of a pain in the butt, wasn't it? I think so. I think it's a pain in the butt compared to this. Okay, two healthy parents have two girls and two boys, and one of those boys has hemophilia. We know that one. We know this one. And we know this one. And all we'd have to do is go, okay, how can two parents have this boy right here? Well, it's going to have to be that there's a big H and a little h that can each come from mom. So she's a carrier. And each of these kids, we don't know. Could be a carrier, could be a not carrier. That's what that pedigree would look like. Does that make sense? So that's the direction we're moving. We're going to stop doing Punnett squares and start doing pedigrees to figure stuff out.
Wouldn't dad have a little H?
Why?
Because they had a kid that was with a little H.
So that's the thing about sex-linked traits is dad basically has nothing to do with it unless it's a girl.
Okay.
If dad has a boy, he gave his Y. So this boy with hemophilia doesn't mean that dad is carrying it because dad gave him a Y. Gets interesting with baldness, boys.
Oh, no.
Well, it means your dad has nothing to do with you going bald. So if you look at your dad and he's like super bald and you're like, oh no, don't say that anymore because it has nothing to do with your baldness. The person to look at would be your mom's dad. Still doesn't guarantee. Still doesn't guarantee it. I think it's pretty complicated. Landon. Oh, I thought you had a question. You were just stretching. Okay. All right. I got a thing for you to do. This is the paper we will be working on for a bit. It has some problems of several types. I'm only going to do a few of them today. All right, take a look. Thing 1 is numbers 1, 2, and 3 on the front side. 1 and 2 should be pretty straightforward. 3 is a challenge. We'll see how you do. The real assignment, I mean, okay, this is the real assignment, 1 and 2, I want you to do those, and then 3, I want you to try. What's going to take you probably the most effort is the pedigree on the back side of this paper. That is a hemophilia pedigree. The shaded individuals have the disease. Your job is to figure out everyone's genotype that you can.
Are there question marks?
There are question marks. Excellent question, Angie. I will not tell you how many yet, because I don't remember. I'm going to have to work it out for myself. I feel like, hang on, I think there are 7.
It says it.
It does?
says it.
Oh, good, yeah.
It would be 7.
Females are the only question marks you're going to have on a sex-linked trait, because males show exactly what they have, right?
You want to do it on a separate sheet of paper?
No, just do it right underneath where the blanks are,
Yeah.
except for put a blank under the female with hemophilia, because I forgot to put one there. Yeah, honestly, what I would do here, first of all, is just do all the males, because you know exactly what they are. Then the female, who's got hemophilia, you know her too. And then use all that you just got for free to figure out the other ones. Okay? That is your homework due tomorrow. 1, 2, and 3 on the front, and the pedigree on the back.